Hi everyone, welcome to the experiment number 6, flow over a sharp-crested weir. If you don't have any idea about weir, so I'm going to talk about what is weir and how can we measure flow using that type of structure. Weir is nothing but an overflow structure that basically is used for flow measuring purpose. Okay, so here we can see a structure, right? Why it is sharp-crested weir? So the top or the tip of the weir is really sharp here. That's why we're calling it sharp-crested here, you can see. So before going to explain in details about weir, so let me just quickly try to explain different types of weir and its functionality. Okay, so weirs are commonly used to measure flow of water, but nowadays the use of weir for the measurement of flow for other fluids is also being increased day by day. So there are different types of weirs depending on the. So let me just quickly show you. If you even can't imagine that the weir is this type of a structure. If for example we have a river, right? This is a river section. We have a water flow, and it is a kind of a channel or canal. It's like 50 meter, 30 meter, 10 meter, whatever the width is, no problem. So we have flow of water. Then what we can do, we can use a dam across the river, right? A dam means if you see that section, so what will happen, that is the bed of the river along this line, okay, and then we are seeing the height, okay, so we have that height here on the flow of water. So then water will flow over this structure, right? But see, we have a length. The width of the river weir is not even minimum. We have a certain width, right? But if it is sharp like that, then it is called sharp-crested weir. So okay, that is weir. It is an overflow structure and it used for flow measuring device. How can we measure that? See, if water flows right over this one, and if we can measure only this height above the weir, we can measure this height, then we can even calculate what is the actual discharge or flow rate. So that is our main purpose. It is so useful, right? If we just use one kind of dam, we don't have to use anything. We have even different types of weir as well. So for this experiment, it will be sharp-crested weir. So based on the structure or the shape, so weirs are different types. You can see there may be circular shape, or there may be this one V shape. So in the next experiment, we'll see flow through a V notch. That is also weir, but that is the most efficient flow measuring device. So we'll do that, okay, in the next experiment. So what we are going to do here, we started from Venturi meter. That is the application. These are all applications of Bernoulli's theorem. Basically, we are applying Bernoulli's theorem to develop a flow measuring device, and we are testing which device is best, right? So far we have seen that our efficiency or the coefficient of discharge is increasing from one experiment to the next, right? So that's what we are saying, and we'll see that for V notch or for this one, when flow will occur this way, then it will be the most efficient device to measure flow, and that device is very useful if you just vary the flow rate from lower limit to the upper limit. So that can measure flow for a wide range of flow rate. So that's what we'll do, okay? So we have rectangular. We can even use a rectangular weir. If our weir is this, it is rectangular. If it is this, it is triangular. If it is that, it is circular. So that is based on the shape of the weir. And there is another classification of weir, that is based on the sharpness of the tip of the weir, right? If we have a section and it is a kind of, that is the height. It is height. So it has a length, right? So it is called broad-crested. If flow occurs right over this one, it is called broad-crested because it has a length of the tip. But if we use a metal sheet like this, very thin, and if we make it sharp like we do for today, so that is called sharp-crested weir. Broad-crested and sharp-crested. So we are just making this tip of the weir as sharp in order to just toss the water, right, with this weir to a line, right? What if water flows over this weir, and if we make this tip of the weir as a sharp, like a blade or anything, so water will touch as a line. Then the interaction between water particle and this weir will be minimum, and our frictional loss will be minimum as well. So in order to do that, we'll use sharp-crested weir. So we'll test different types of weirs, but not in fluid mechanics session. In open channel flow, we test that broad-crested weir because it needs a experimental setup wider than this one, and we can do that. So okay, so that is called weir. Is an overflow structure, and it has different shape. Based on that shape, we can even classify it according to its sharpness, sharp-crested or broad-crested. Today's experiment is basically flow over a sharp-crested weir. Why is that? The crest is sharp. So we have a metal plate like this one. You can see the block. So it has it has a height P, and if water flows, right, these are the streamlines. So what is actually happening? Water is trying to converge right here. The streamlines that are lower than the height of the weir, it is just trying to converge here, and then they are flowing. Okay, you can see that. So what is actually happening here? So there you can see there are some vortices or some circulations here. So these water won't be flowing over this weir anymore. Okay, so that's why this is basically dead zone. So these are dead zone. So we are not concerned about that dead zone. Other than having concern about that zone, we are gonna focus right on that part. So we have to assume something in order to derive a relationship in between this H and the actual flow rate QA. So as before, we'll calculate the actual discharge, but not here because it is a channel and we can't even measure, we can't even put any bucket to hold the water. Other than doing that, what we can do, we can use a flow meter. We have a digital meter, so that can measure automatically how much flow is actually flowing right over this weir. We can measure that. But what we'll do today, we'll derive an equation that can calculate QT. And once we have the QT, we can calculate the efficiency, CD, right, the coefficient of discharge, and from that equation, as before, we'll derive that relationship QA is equal to C H to the power n, and we'll plot we'll plot basically one log graph, and from that graph, as before, we will calculate the value of C and the exponent of n, right, similarly. And today I'll show how to plot that graph. If I get time, then I'll also show that. It is pretty simple. If I just plot it in Excel, it is pretty simple, but you can even use any graph paper, log graph paper, and then you can plot that as well. So let me just quickly derive that one. And assumption for deriving this relationship in between H and QA or QT, whatever it is, what is actually happening here? See, the streamlines are converging, and see, it is also showing this, following this line, and sloping here. It has a downward trend. It has x component of velocity, y component of velocity, and for these streamlines, it has also same x component of velocity and y component of velocity as well, right? So once we have this x component of velocity and y component of velocity, and because of that, it is converging here, and it is just contracting. So we have a special name of that streamlines when it is flowing over this weir. We call it nappe. And then we have this contracted streamlines here just under this nappe. Then we can call it contracted nappe because of this particle component of the velocity right under this nappe. We have contracted nappe, and we also have contracted weir if our weir is the length of the weir is less than the width of the reef. It means we have a reefer cross section like this, and we have a weir here. So that is the width of the weir, that is not covering the entire width of the river. Basically that is the length of the weir, we can call it the width of the channel or river. So if the width of the channel or canal or river is greater than the length of the weir, then what will happen? We'll have the streamline will flow like this way. So it won't cover the entire edge of the opening, or the this is basically the nappe. We can see from the side view it will be like this. So that is the streamline, these are the streamlines, it will flow like this way. So we have even end contraction. So then the length, it won't be the length, actual length of the weir, rather it will be less than that. So we'll calculate that one, what will be the length of that one. So we'll calculate. Okay, so for the time being, for deriving the relationship in between this h and flow rate, we have to assume, even though the streamlines are not parallel to each other, but we are going to assume that okay, these streamlines are parallel to each other. Okay, so what is actually happening? So upstream of the weir, the flow is uniform and the pressure varies. Right here, the flow is uniform, streamlines are parallel to each other here. So we are assuming okay, we have the pressure that is hydrostatic like this, we saw that, right? But in reality here it is assuming P is equal to rho g h, if there is the h. So we are assuming that the flow, whatever the flow shape is, or whatever the shape of the nappe is, at the upstream of the weir, the pressure should be hydrostatic, right? And the free surface, so they're talking about that free surface, it should be horizontal, right? But it actually it is not horizontal after passing that weir. It is just, right, it's converging and it's downward. But we're assuming after passing that weir or just over the weir, the streamline should be parallel and the surface should be horizontal. That is one of the main assumptions, right? We're assuming that one. And there is another one, the pressure throughout that sheet, that nappe, it also should be hydrostatic, right? But in reality it won't be that, it will be different than hydrostatic pressure distribution, right? And the surface, of course the surface should be atmospheric, in atmospheric pressure. The effect of viscosity and the surface tension should be neglected, but in reality there will be surface tension and water is viscous. We know that the viscosity of water changes with the change of temperature, we know that. And the upstream approach velocity is neglected. That is the most, I think, most important assumption that we are going to make here, that the upstream velocity, see, water is coming with that velocity and then passing over it, but what we are assuming that this velocity is 0, but we are assuming the upstream velocity is neglected. We have to neglect that velocity, then we can derive that equation, what we are going to derive. So we have 0 velocity here, then what we can do, we can apply our Bernoulli's principle. But because of that assumption that in reality water is converging, the surface is not inclined, that's why we have to measure this distance h from this weir at around 6 times of the height, right? This height. If we can just measure like 5-6 feet away from that weir, then we can get a perfect horizontal surface of the water. Then our reading will be more accurate than inclined surface. And still, since the water flow will be like higher, then still there will be some undulation right here. So we have to take average measurement. So these are the assumptions. The pressure should be hydrostatic and the surface should be horizontal. Water should be the viscosity, effect of viscosity and surface tension should be neglected here, and then the upstream approach velocity is also neglected there. and then we are just drawing. So let me just quickly derive the equation here. What we are doing, basically we are drawing the same long profile. Water is here flowing, right? We have water that has this profile or shape, you can see here. So it is flowing over this weir, and then it is flowing this way, and then we have this type of thing. If you are familiar with this one, so I'm gonna talk about this one as well. So what is actually happening here, see, just above the weir, the water surface is not horizontal. That's why we are using that 6/8, right, at the upstream. Then we can measure, then we'll have horizontal surface, and our measurement will be okay. And then see, that is the nappe, it is flowing, and if it is free fall, then definitely under this nappe we'll have empty space, that will be blank. So we have to make this space, we have to use one pipe to ventilate it. Once we ventilate this one, so that will be atmospheric pressure, and we can see this is a free, right, this is a free space. And then the water will fall on the surface on the downstream side of the channel, and then the flow will be supercritical. We know what is the subcritical, critical, and supercritical flow. If we calculate the Froude number, then if the Froude number is 1, then flow will be critical, and if the Froude number is greater than 1, then the flow will be supercritical. And if the Froude number, right, FR, is less than 1, then we call it subcritical flow. Most of the river flows, these are subcritical flow. So here we have subcritical flow, here we will have supercritical flow, and then we have transition from supercritical to subcritical again. And then if you just make a transition from supercritical to subcritical, there will be a hydraulic jump. We call it hydraulic jump. So that is another topic, so we're not gonna discuss that in details here. It is basically a subject that is taught in open channel flow, so we'll talk about that in open channel flow laboratory section. Okay, so here what we are assuming, so the height above this weir, the height of the weir is P, and the water depth above weir is h, small h, because it is changing. It may change if you change the flow condition. If you increase the flow or decrease the flow, h will increase and decrease, right, consequently. And then we're taking a section here, you can see we're taking a section here, this section is that red box. We're taking that section, and what we have to do, we have to measure the flow rate, right, for this height of the water that is flowing over the weir. So if we can measure this one, why it is h, see, the section is horizontal, you can see the section is horizontal here, and it is even rectangular section. So we can easily calculate the cross section, and if we know the velocity, we can even calculate flow rate. We know that, right, from continuity equation, Q is equal to AV. If we know the area, we know V and H, then we are done. No, it is not real, but we have to know the velocity. This velocity will change. If the particles are here, the velocity will be different, and if the particles are here, velocity will be different. That's why velocity is a function of depth of water, because we have pressure head here. So that's why we have to apply our Bernoulli's principle in between 2 points, right? Point number 1, where here, just where the streamlines are parallel and the surface of water is perfectly horizontal. And then we are gonna put another point, because we are assuming this point is also horizontal. So we have 2 points, but other than putting this point here, what we can do, we can see the cross section here. That's why it will vary, and we are assuming that we have taken this height as h, that would be our total height above the weir, and we are taking this small strip, and that is the small strip we have, and we know the total length. If you know the width of the river, so that is the total length. Okay, that is B basically. if that is the width of the river flowing, and we are seeing the long section, that is the long section, and we are basically making a small slice, okay, infinitesimal slice. So it is called dH, since the depth of water is changing, so it is called dH. So we have that dH. So what we can do from this small strip, we can calculate dA, right? What will be dA? B, we know the width of the B is constant because the width of the river is not changing, B is constant. However, the strip, the height of the strip is changing, it is dH, so that is dA. So what will be the flow rate through this small strip or through this slit? It will be dQt, because we are applying our theory here. That's what is dQt, infinitesimal discharge from infinitesimal cross-sectional area. So that will be, that has to be dA and V, right? This V through this section, that will be V. If we assume, okay, this section is located h, right, that h meter from the top of the water surface, h is variable, then it's here, then we have to apply the Bernoulli's principle in between this point and the surface of the water. So that's why if we apply, that is point number 1, that is point number 2, right, that is point number 2. So if we apply Bernoulli's principle in between this one, Bernoulli's theorem or principle in between point number 1 and 2, what we'll get? For point number 1, the velocity is 0 here. The velocity is 0 and the pressure is atmospheric, that will be 0. What we'll have? Only we will have the elevation, that is h, right? If we consider that is our reference level, from this reference level, this point 1 is located h meter or feet above that reference level. Then it has to be equal to what? Equal to the total energy at point 2. At point 2, it is located at the same point, it is there, and what will happen? Since water is flowing with a velocity, we'll have the velocity, right? And this surface, what? It is basically on this nappe, it is also over that atmospheric pressure, so pressure head will be 0. And from this relationship, the same relationship we applied for now the previous experiment, right? Previous 2 experiments, the same thing. We have 1 point on the tank and we have 1 point on the center, right? Or for the pipe, it was there. Okay, so we are applying this same formula, and from this one, V is equal to 2G H, and there it was 2G capital H, but here the H is changing with that velocity. So now we have the infinitesimal flow rate, dQt is equal to dA. dA means B dH, and V for that small strip is nothing but 2G root over 2GH, right? So we have that. Let me quickly clear this thing and let me drive that equation. So we have that dQt is equal to B root over 2G, and then we have h to the power half if I just simplify, and then dH, right? These are the constant we have. So if I want to get total flow rate, right? Total flow rate for this part, just height, total height of the water, means for the entire height, we have to make many, right, slits like this one, many strips, and we have to add them up. If we add all these things together, and if we calculate the velocity like this way for this slit, for this slit, for this slit, then we can add them up, then we'll have total QT. So other than doing that, we can right, we can apply our mathematics integration. So what we'll do from 0 to QT here, and here what we are changing, when the depth of water is here, it's 0, and since the depth increasing, right, up to the top of the weir here, top of the weir, it is from this to top of the weir up to capital H. So then the upper limit will be capital H. Okay, so that's the logic here. and we have to just integrate this equation. It's pretty simple. We will have a qt, and then here we have b root over 2g, and we can write one more line, h to the power half and dh. So these are the variable, and b root over 2g, and we know the integration of, right, x to the power n and dx. So it is nothing but x to the power n plus 1. The power will be increased by 1, and we have to divide the same increment n plus 1. So that's the, so here we have the power of h is half plus 1 divided by half plus 1, and we have to use our limit of integration this way. And then b root over 2g, so what will happen? H to the power what? 3 divided by 2, and then 3 divided by 2, and we still have the limit 0 to h, right? And we can apply that. B root over 2g, since it is a limit, this 2 by 3, 3 by 2, we can just put it here, 3 by 2, it will be reversed, and then we still have h to the power 3 by 2 and our limit 0 to h. Okay, and now we can apply our h. We have 2 over 3 and root over 2g, and then we have b. I'm just rearranging, and what we will have if we apply the limit, we can replace that variable by that limit, h to the power 2 by 3 minus, right, 0 to the power lower limit and 3 by 2. And if we further simplify, we have the final equation, 2 over 3 root over 2g and b and h to the power 3 by 2. So that is the final equation, theoretical equation, right, from which we can get our total qt for the total height h. This height must be measured from the top of the weir. We don't need to know the height of the weir every time, because we don't know the depth of the river. We don't need to know that. If we know the height, right, because while designing that weir, we'll know the height, right, from the bottom of the channel or from bottom of the river. And once we have the information, we can use that information, and then we can measure the total height or depth, and then we can reduce. Since we are measuring the depth from the bottom of the channel, we have this weir. For example, here we have the weir, we can measure the total depth, right, from this one is prime. Then we need to know only capital H, so we have to deduce h minus p. The height of weir is p, right? We need only this one, the water, because we derived the equation based on that formula. So once we have this equation, we can calculate our theoretical flow rate over this weir, and we already have that actual flow rate from a meter. Today we will use a flow measuring meter, that is a digital meter. So that digital meter will give us the actual flow rate, because it is a channel, big flume, water will flow, and the volume is huge. Flow rate is bigger than what we saw previously, so that's why we don't need to even calculate manually. We won't be able to do that, because water will be circulating, and then we'll measure, because that will take time, and it will be huge volume of water, and the flow rate is pretty big. So we can calculate that way, actual flow rate and theoretical, and after that we'll have CD is equal to QA and QT. Similarly, we need to derive that relationship again. QA is equal to CD, and QT, QT means 2/3 root over 2g and b and h to the power 2/3. Again, this part is constant for a specific weir, right? The width of the weir will be fixed, means the length or the width of the river is same, and 2g root over 2g, it is also constant for, right? We know that g is constant, 2/3 is constant, cd is also constant for a specific weir. So we can replace that part with c, and then the power of h will be unknown, n. So this time it is 1.5, but previously we saw it was half, but now we know the theoretical n, the n from the theory, the exponent of h is 1.5, but we have to be able to calculate the n, but we know that it should be some, right, 1.45 to 1.55. that is the acceptable limit. We can, and if it is close to 1.5, then it's good. But if it is perfectly 1.5, that means your experiment is wrong, because you can't make theoretical relationship, right? So it has to be other than 1.5, but it must be close to 1.5. So we'll calculate that one as before. That is called calibration. We'll calibrate this. Okay, so let me quickly show you that. And once, see, I just mentioned this one. If we have any weir, that is the length of the weir. If the width of the river is this, and if the length of the weir is less than that, then we'll have end contraction. And for end contraction, the actual width that we have to use in that equation, that B, right, that QT is equal to 2/3 root over 2G and B, and then H to the power 2/3. So that B won't be similar to the length of B. It has to be less than. So it will be B prime equal to the actual width minus 0.1 NH. So the number of N contraction. If we have 2N is contracted here, N will be 2 and H is the total height we just saw. But if we have one side contraction, right, like this way, we have a weir like this way. So we have contraction here, right? We have contraction here only one end. Then we have to use N equal to 1. But most of the cases we will have this type of N contraction, right? The weir will be locating at the middle of a channel. So that is another case. So then our equation should be revised like this way. We'll have, right, we'll solve one mathematical calculation, then we'll understand what is actually happening. Okay, so let me quickly show you that. So our main objective for today is observation of the nappe for ventilated and non-ventilated condition. So we have to use one pipe in order to insert air so that it will now fall freely. Then the flow rate will be increased, and we'll find as before that CD, and we'll plot that QA versus ACE in a plain graph paper. We'll see that, and then we'll calibrate the instrument. And here let me just quickly cover this one. What are the assumptions made in deriving the equation, and what is the extent, right, of their validity? So what we did, we assumed that water surface is horizontal, pressure distribution is hydrostatic, right, rho GH, and we neglected the approach velocity that is at the upstream of the weir, and we even neglected the viscosity and surface tension of there. Definitely they have there will be some, their validity is limited if you just use that extensively, and if you consider still in practically we are using this relationship and it's working, so their validity is okay with a wide range of variety. Okay, so it is valid. And why the pressure distribution over the weir crest is less than hydrostatic? Definitely because the weir crest, we have the weir, we have the sharp-crested weir, right, and it is flowing this way, it won't be hydrostatic because the pressure, right, we have velocity here, we have velocity, but we don't have any what here. We also have height h, but we don't have velocity. If we apply the total energy, we have velocity here, we don't have velocity. The pressure, we are assuming hydrostatic everywhere, hydrostatic, but in reality it won't be hydrostatic because see, it is converging, and these are also converging, and we have nappe here, we have air trapping under this one. Because of this reason, the pressure, it is mentioning here that the over the weir crest it won't be hydrostatic because of that inclined surface. And then what is the effect of rounding the weir edge, right? If we round or if we make the weir edge as sharp, then it will make less contact, minimum the contact in between water and the weir will be minimum, and then our head loss will be minimum, it will be reduced, and then flow rate will increase. Our main objective is to increase the flow rate, actual flow rate, right, to reduce the loss. By reducing the loss, and that will increase our actual flow rate. And then why it is necessary to ventilate the space below the nappe? Here we have to use a pipe that will enter, that will, right, allow air, and it will be empty. So water will flow freely, and then we'll have increased head there. And if we have increased value of h, then our equation says, okay, our flow rate will be increased. So that's why we need to ventilate. Otherwise, if we don't ventilate, water will be everywhere, and then it will be kind of submerged, and we'll have pressure, right? We'll have pressure from downstream, and this won't be like the head we had when we have ventilated condition. The head will be reduced, then flow rate will be decreased, right? That is not our main point. And then discuss the effect of lateral contraction in case of contracted weir on the flow over the weir. So that's the thing, contracted weir. Once we have a weir that the length of the weir is less than the width of the river, then we will have end contraction, and because of the end contraction, the flow will be reduced, because we are having flow this way and we are not using the entire length, right, or the width of the river, and b prime won't be b, it will be reduced by this amount. So that's why our flow will be reduced. So that is another problem. And then we have the mathematical equation. Let me solve that. A rectangular sharp-crested weir is 3 feet height. We know that, right? Rectangular sharp-crested weir, the height means p, the height, right? We have the height, sharp-crested weir. We have the height, that height is p, 3 feet, okay? Extend across a rectangular channel, okay, which is a rectangular channel which is 8 feet wide. When the head is 1.2 feet, the head over this one, it is 1.2 feet. Find the rate of discharge by neglecting the velocity of approach. See, a rectangular sharp-crested weir, p is this, and rectangular channel which is this wide. So they didn't mention that is it contracted or not, because we don't know the width of the weir, we know the height of the weir. So we know h is equal to 1.2 feet, and we know the b. So for this case, b is same as the length of the weir, it is 8 feet. So we can quickly apply our equation, 2 over 3 root over 2g, right? And we have b, and we know h to the power 2/3. And if we just calculate quickly, 2/3 root over 2 into g for FPS unit is 32.2, and we know b is 8 here and h is 1.2 to the power 1.5. If I just quickly calculate what we will have, we'll have root over 2 into 32.2, and then I'll have 8 multiplied by 8, and then we'll have 2 divided by 3, and then we'll have another one, 1.2 to the power 1.5. So here 56.26, that's the feet per second. So that will be the flow rate if we have this condition. So this is how we can solve any mathematical equation. So let me just quickly go to that data set as before. So see, as before, we have what we have to measure. We have to measure the width of the weir, or the width of the channel. It is same since it is not contracted. So it is 12 inch, means I converted it to centimeter. It is 30.48 centimeter, right? If you see one scale, that is 1 feet, and we have 30.48 centimeter. And the height p is 6 inch, that means 15.24 centimeter. These are the measurement, that's why it's in bold. And then the elevation of bed level at the beginning, the bed level here, because we are using this weir at the bed level, this one, it is 0, and we are measuring here finally final bed level 24.66. So if we reduce, or if we deduce that value of p, we will get the value of h, right? So we are measuring that h is this one, so we are getting 9.42. So let me just quickly fill up. See, we are taking this measurement, nothing else, and we already have that QA from our flow measuring meter, digital meter, and we have different groups. We are changing the flow condition. So for this group, it is 9.42, this one. So the actual flow rate we're getting from our device directly. You can see this is displaying there, and we have to calculate CD. So before that we have to calculate that QT for this one. Okay, so we just saw the same equation, 2 over 3 root over 2g, mean 2 into 981 because these are in centimeter, and then B is what, 15 point, not 50, 30.48. okay, 30.48, and H is 9.42 to the power 1.5, or 3 divided by 2. So let me just quickly calculate. 2 divided by 3 multiplied by root over multiplied by, okay, 2 divided by 3 multiplied by root over 2 into 981 into B, 30.48, okay, 48, multiplied by the height 9.42 to the power 1.5. So what we have 260.53. so that's the calculation we have. And if we calculate CD is equal to QA divided by QT, if we divide this 18,000, right, 18,000 divided by this value, we are getting 0.69, this 69. So we are filling up this table for different flow conditions and for different groups. So we have this. So now what we have to do, we have to plot this value with that value, and we have to calculate, right, because we derived that equation C is to the power n. So let me show you that. I already plotted, so I'll show you how to plot this in Excel using that value. And here is the line, so we can read, right? So I marked this red mark here again, the first, okay, the first point, this point, and that point. So we have 10,000 here, 10,000, but the value of H, the head here, it is 1, 2, 3, 4, 5, 6. That is 6. That is 7. So that will be 6.2, maybe, okay, 6.2, and the actual flow rate is 10,000. That is 1 point, and we have another point here. So we have 10. We have 10, the value of head 10, and then we have what? That is 10,000. That is 20,000, 30,000, and then we have 100,000. So that will be 20,000. Okay, and if I apply, okay, 20,000, and if I apply that equation of the slope, n is the slope, then we can know, right, we know that q log is equal to qa1 divided by qa2 and whole divided by log h1 divided by h2, and then we can even use the value log 10,000 divided by 20,000, right, and whole divided by log 6.2 divided by 10. So that will be half, log 0.5 divided by log 6.2 divided by 10. So it should be close to 1 point, right? I have 1.44999, so I can take 1.45 because I plotted it quickly. That's why still it's okay. I didn't check. I'm checking for the first time. So I have that value, and I have to calculate the value of C, right? We know h to the power 1.45. I can use 1 point. This first point, I usually use that one. So I have 10,000 here. Then C is unknown. I have 6.2 to the power 1.45. So what will be the value of C? We know that, right? 6.2 to the power 1.45, and we have to divide this. Okay, so we have 709.64. So here is the calibration equation. QA is equal to 709.64 and h to the power 1.45. So that is the calibration equation. If you write this equation on the channel or flume where we have the weir, then someone can measure that h and use calculator to calculate this one. So other than doing that, it's time if you use this equation to plot a graph, the relationship between, right, if you plot QA here and if you plot h, then it will give you graph, right? Either this way or this way. We'll see that, and then someone will read directly from this one. So that's that. So here I have plotted. I use that formula, and I use several values of h, like 5. I used 3, 0. I use first 0, 3, 6, 9, 12, 15. This is how I just used the value of h, and I calculated the value of qa, and I plotted it, and it's showing like this way. So now if you just paste, if you plot this one, if you paste this graph, right, just on a board or anywhere, somewhere close to that Weir, and someone will come and then they will take the measurement, like he has a measurement of h as 10 centimeter, then he will directly read that graph, and he will get 20,000. Okay, he will get 20,000 centimeter cube per second flow rate. He doesn't need to have any calculator, and no one needs anything to get the actual flow rate. So that is the calculation, right, we have to do before just making that Weir as operational. So this is how we can measure the actual flow rate. Okay, and we already know the derivation processes, and we already have idea about how to calculate the actual flow rate and theoretical flow rate and CD, and how to plot this one. So let me just quickly show you how to plot this graph in Excel, because I already demonstrated that one, but someone may be curious about this, that okay, I'm just showing everything ready, but you may not follow this one. Okay, let me just quickly switch to my desktop, and then I think you will have that idea. Okay, that is pretty simple, not a problem. Okay, so if I can share my screen, and let me just show you that it is possible to show you. Maybe I have okay, don't have to be worried about that one. I'm just opening a new Excel file. What I have to do, I have to open that data sheet. Okay, once I have the data sheet, then it's possible, right? Once I have the data sheet, because I have the data sheet here, I'm just copying this data sheet and pasting it in the Excel. Here I have to have this head. Okay, I need to have this head. I'm copying it to there. I need to have the actual flow rate, and it should be in the not there, should be in the QA. Okay, that is QA. It should be along y-axis. So I'm just selecting that one and inserting, nothing else. I did it right long time ago, and I'm using this one. So that is not the log graph paper. So what I have to do, I basically have to use log, right? So I'm just extending it a little bit this way so that you can see, and I'm just modifying from home and using that automatic color, and I'm just increasing it pretty quickly. That should be 14 so that you can see that, and I'm using the Times New Roman, and that will be head, right? Head difference, that is in centimeter, and that is the actual flow rate we have here. Actual discharge, basically centimeter per second. Okay, so then see, right click and then format axis, you'll have here logarithmic scale, and you can change it from 1 to 10. You can set, for this case it is okay. I'm right clicking and adding minor grid line, so now we can see. And for this case, same, I'm using logarithmic scale, and it's bigger than this, so I can start from 100. Okay, the lower limit should be 100, and then we'll have the graph here. If you start from 1000, not a problem, it will be okay, it is there. If you wanna see that minor major grid line pretty quickly, you have to go there, change the color, it is there. Right click, format minor grid line, and then change the color to this. we'll have that. Okay, so format minor grid line, color change, this way you have that. So what do you have to do? Go to insert, and then from shape you can even select one line. This line has to be average line that will pass right through most of the points, and if there are some points that are not on the same line, so you have to put that point somewhere in between, right on the left side or right side, whatever it is not a problem. So once we have that, I can even highlight that. I can change the color, I can even change the width of the line. Usually I'm using that one, and from this you have to look for this cross section, right, crossing point, and you can even highlight that way. That is pretty simple, right? For example, I usually plot it that way. I change the color to red, and then I increase the weight here, and this is how I did it, right? I highlighted this way. You can do that as well. I'm just displaying here pretty quickly because I need to even change that. That is pretty a little bit different than what I actually have. I'm quickly showing here, that's why, because the line is not accurate enough now. It will be inclined a little bit, and you can even change. Okay, if it is not, you are not satisfied, you can quickly change the inclination of the line. At first you have to do this way. Okay, so you can do that. So this is how we plot it. I plotted the line. Someone may ask that one, okay, how did I plot this one? So this is how I plotted. Then here we can see the plot. Okay, so that's that. And if you have any query, so in the next tutorial we'll even use another most efficient flow measuring device that is called V-notch. So that has a 0 width of the base, so that's why that is the most useful flow measuring device. And then we'll cover our friction. So we'll have we have to even finish 3 more experiment. So this is basically experiment number 6, and we'll cover up to experiment number 9. So then the entire course will be finished. So there will be some other experiment like pump and the demonstration of vortices. So if I get time, that is extra, so I'll try to show that, no problem. So try to even reproduce what I've demonstrated today or for other experiment, and if you go through all of this experiment, you will have a clear idea. And if you have any query, you can ask any query, or you can post anything to your instructor. If it is online or if it is offline, you can directly ask for any clarity, ask for any solution of your problem, or you can have any question, you can post it there in the comment box. So later on maybe I'll be able to answer that question if I know that. So thank you very much for watching this video, and thanks for learning new things. And hopefully I'll see you in the next tutorial. Until then, stay safe. Bye.